My name is Chi Ming Chen. I'm from National Taiwan Normal University.
My name is 张明哲 from 师范大学。
My name is Li Weijun from National Taiwan University.
Is Chosen Zhu from National Taiwan Normal University.
Ji Hao from National Agriculture Education.
Thank you. Now we follow with the introduction of each team, including your team member and the title of your team, if there's something interesting. Begin with the reporter.
We are team new addition and 李承旭、李家祥、李义柔、陈一晨、高志荣。Thank you.
Your addition, what does that mean?
Means to be smart.
Okay, thank you. Now it's your turn.
Honorable juries and fellow students, we are Team MD fresh from Mingdao High School, and my name is Wang Zhenhe. He is Chen Pinhan. He's Yang Xiangyu, and then he is Jiang Junhao, and he is You En. Thank you.
Thank you. Finally, the reviewer.
We are grade 2, and this is Yan Zili, Yu Xuanchen. Oh, you can also call him Wang Xiamin, and Hong Weichen, and Liu Yucheng. Thank you.
Okay, let's begin with our stage 1, which is the challenge from the opponent to the reporter. Yeah. 1 minute before you address your question.
We would like to challenge problem 1710 helicopters.
Reject or
So what's your decision? Okay, thank you. Now, the representative of each team, please write down the name for those who would take the floor. 刚是怎样？
是刚刚他们没有说，或者是我没有听到声音有点小，他们没有说 reject or accept。
那所以就相当于本来还有一点时间，就直接跳。OK。
他刚出什么事？
没有回复啊。
那为什么少了900多？
说 OK 或不 OK。
不是，但是照讲应该是1分钟结束，他们才有义务一定要讲的。意思说他们看起来是还有几秒钟是可以再讲。对，那所以是误判。
为什么跳到900？
对啊，就为什么这样？
就是他时间超过之后，他的
刚有超过。
对，就是他时
也是
间
1分钟。
对，1分钟时间到，
已经到了。
然后就是他就有可能会跳掉。
不是，如果我刚看好像还有半圈的。
我也看还半圈。
对啊，没关系，就注意一下。 Okay, it's a time for the presentation of the report.
Greetings, fellow competitors, honorable chairman, and juror. Lovely morning to you all. I am from Team Erudition, and this is our report for question number 17, hand helicopter. Now, for the outline, first of all, we have introduction and problem statement, the observation video, the theory, the setup, experiments and observation, and then at last we have the conclusion. Now, for the introduction and problem statement, a simple hand helicopter can be made by attaching rotor blades to one end of a vertical stick. The helicopter moves upwards when the stick is twisted at a high enough speed and then let go. Investigate how the relevant parameters affect the lift-off at the maximum height. Now, the key points of the observation for this problem statement is that how does different lengths of the wings dimensions affect the helicopter's motion, and how does the angles in which the wings are twisted affect the helicopter's motion. Okay, now for our observation video, you can see that when you spin the hand helicopter, it goes up a distance and then drops down. Now for this video, it is the same, just not in slow motion. This one is in slow motion. So basically, these two describe the phenomenon. Now, for the theory part, first of all, you have this helicopter system. Now, hand helicopter is basically this part without the motor. So the motor is your hand when you spin it. Now, you can see that it has a thrust upwards that pushes the whole hand helicopter from a direction straight up. Now, for Newton's third law, all forces between two objects exist in equal magnitude and opposite direction. So basically, for an airfoil, which is presented as the wings in our hand helicopter, you can see that the air, which is entering the direction of the airfoil, one part is pushed up and one part is deflected down. And the deflected downside actually pushes the ground, in which creates another force that pushes the airfoil up, which is one of the reasons which causes the airfoil to fly. Now, for Bernoulli's principle, we can use this equation to describe a steady incompressible fluid flowing through a ambient system. And through changing the constants, we can get these two, which is basically just a variant of this one, that you can have different variants. Now, another one for Bernoulli's principle, we previously mentioned a steady incompressible fluid. Now for a steady compressible fluid, we have to consider the pressure throughout the fluid itself. That's why we use integration and write dP and rho, which is density, as a function of pressure. And then we integrate that from P to P1 and plus psi, and which psi is the potential associated with the conservative field force, which in normal systems we only consider the gravitational force. But if you're looking at a quantum-sized ambient system, it will be electromagnetic force constant. And then we can insert that into the ideal gas in an adiabatic system, which will be V squared over 2 plus Gz plus gamma over gamma minus 1 P over rho, when gamma is the ratio of the specific heat constant to water. Now, if we omit change in elevation, because we all know that the fluid has a certain volume, but when you compress it, the volume changes. So if we omit that, then we can get the equation as follows, which basically we ignore Gz when the change in elevation of the liquid is not very significant to the elevation of the environment itself. Now, if we want to quantify lift force, what would we do? There are basically two kinds of things that you can do. First of all, the harder one, integration, well, harder but not actually that hard. Integration of pressure. You basically want to do this. L is the lift force. So basically, P is the pressure distribution on the wing surface. So basically, picture this. You have an airfoil, but the pressure distribution on the airfoil is not constant. So basically, you want to calculate the whole thing, the whole surface area of the airfoil, the whole pressure on the airfoil. So basically, you will have to use integration. And then P times N times K times ds, in which N is the unit vector horizontally, the vector that is entering the airfoil itself, which is, like I just mentioned, like if you have a wind that's blowing onto your airfoil, one would go up and one would go down. That is what N describes. And K is the vertical unit vector, so basically that's what describes Newton's third law of motion, the one that pushes the airfoil up. And then ds, yeah, S is the area, in case you're wondering. Yeah, please. So basically, now for the easier one, lift coefficient formula, which can be written as this: L equals 1 over 2 rho V squared times S C of L. Now, the requirements, oh well, yeah, basically, you will need the density, you will need the velocity in which the airfoil or the wing is moving, you would need the surface area of the airfoil, and you would need the what we call a lift coefficient. Now, the lift coefficient is kind of a weird thing because you need to consider so many things. You need to consider the air humidity, the air pressure. It's just way too complicated. So basically, we will want to just combine these three. Desired angle of attack, which basically, you know, the angle of attack is what we just mentioned in the problem statement, the angle at which the wings are twisted. So basically, it's like this. So you have an airfoil right here, right? Now there's an angle. This is the center of mass, and you have a flat surface. This is the horizontal axis. Now I know that's not horizontal, but okay. This is the horizontal axis. So basically, you have an angle right here. Let's call it phi. Now phi is the desired angle of attack, and what we just mentioned, the angle that we want to know. How does it affect the motion of the airfoil? Now, the Mach number is the fluid velocity. In this case, the relative fluid velocity to the airfoil, which would equal to the relative velocity of the airfoil to the fluid if you do not consider directions. Basically, you just compare that to the ambient speed of sound, which is, yeah, you know, like 331 plus 0.6t. That's like not an accurate function at most in most environments. Then we have Reynolds number. And not Reynolds. Reynolds number is the ratio of inertial forces to viscous forces within a fluid, which is the air that we're talking about. Now, the relative inertial movement, well, you need to consider both of the forces because it can lead to different fluid velocities in different parts. Now, for our setup. Now, we have to measure the lift force caused by the propelling wings. So we 3D printed wings, attach the motor, and attach the balance point, which is basically a stick. Now we have an electronic scale right under that, and then we have batteries to switch, and then this that connects to that. Now, experiment and observation. So basically, we want to set another something to measure that. So we have 2 batteries in a series circuit and 4 batteries in a series circuit. If you learned this in middle school, you will know that the voltage is actually 2 times of this one. Now, phase 1, we want to change the length of the wings. Phase 2, we want to change the width of the wings. Basically, we're just messing around with the dimensions right here. Now, phase 3, you want to change the angle of attack, which is, between the wings and the horizontal axis, as I just previously mentioned, the angle phi. Now, 2 AA batteries with a series circuit and 4 AA batteries with a series circuit. Yeah, I apologize for this picture quality, it's just, Now, we have 3 different lengths of wings. We range the width as 1.5 centimeters and the angle as 10 degrees. So basically, this is a computer model. We have 7, 9, and 11. This picture is created by SketchUp, the Google thing. Now, the 3D printed models right here are 7, 9, and 11. Yeah, okay, that sounds weird. Now, for the 2 battery series contact, you can see that the lift of the average lift of 7 centimeters is 0.8154. The average lift for 9 is 1.0838, and the average for 11 is 1.037. I'm talking about the last column right there, lift. That average is like the weight, And so for 4 batteries, you can see that it was basically like really close to double of what was 7, 9, 11. Now, force of lift corresponding to length of wings. You can see that this has a slope gradient that goes up. This has a slope gradient that goes slightly down, but not that much. And this one is basically one of 2 times of this one. Now we have 5 different lengths of wings, and the length is 9 centimeters, and the angle is 20 degrees. No, actually that's 10. That's just that's a typo. 1.5, 2.0, 2.5, 3.0, 3.5. Same right there. SketchUp. Now 2 battery series contact. 1.5 is 0.9086, and then there's 1.1008, 1.3866, 1.0976, and 0.8154. Now for 4 batteries, it's basically the same. It's just like, because it directly corresponds to the area the surface area of the airfoil itself. Now, you can see that it encountered a significant drop after 2.5 centimeters. We will talk about why later. Now, 4 different angles. We have 9 centimeters and width as 1.5 centimeters, 10, 20, 30, 40. Now, the angle, just read it yourself. 10 degrees, 20 degrees, 30 degrees, 40 degrees. And, no, come back. That is basically, it's, kind of 2 times of that because we just mentioned 2 batteries, 4 batteries, 2 times voltage, 2 times RPM. Now, the force of lift corresponding to the angle of wings, you can see that after 20 degrees, it encountered a significant drop. Conclusion, 1. So, lift force encountered a drop with 11 centimeter long wings, and same with the width, because we think that the wings are too heavy because the surface area was too big, so it was not going to reach full thrust potential. Next one. We just talked about that. Lift force encountered a drop of 30 and 40 degrees. As mentioned in this graph, we think that it generated more drag force than lift force. Drag force is basically air friction, air drag, air resistance. And that's all.
Time is up. Now we have 2 minutes for the opponent to ask the question.
Hi, well, juries and fellow students. This is the opponent from Team MD Fresh. So first of all, I would like to ask the parameters of your experiment. So are there length, angle, and width? Is that correct?
Yes.
Okay. And can we go back to the phenomenon video?
The video.
Yeah, the video. Can you play this video again? So as you can see, the helicopter goes back towards the place where it let go of the hand helicopter. Can you explain why this happened?
Well, I think it's because that when we release the hand helicopter with actually our hand, we actually exert an extra horizontal force upon the hand helicopter, so that may cause some other kind of motion, but that is not to be discussed within the problem statement.
Okay, so you use your hand only for observation.
Yeah,
not for
observation.
experiment.
No.
So for experiment, you use a motor. So how exactly does that work? Motor works.
The motor is attached onto a plastic piece which is glued to the motor, and when the motor spins, the plastic piece spins, right?
And pulls the helicopter.
Yeah, it propels the hand helicopter. It propels the wings that we 3D printed.
Okay. Can you? I have another question, which is how did you check the height of the maximum height of the helicopter? Because in your setup you didn't mention of any tracker or any any tractor or any camera stuff. So how did you exactly measure your data?
Wait, what? Can you say that again? I'm sorry.
How did you measure your data? Because you
Which
didn't
data?
have all of the data.
All of the
Because
data.
you didn't, can you go to the setup page?
Yeah, just go to the setup page.
Okay, time is up.
Okay.
You have 3 minutes to prepare.
他们刚制作。
Okay, it's a time for the opponent to take the floor.
Okay, so there are some technical difficulties, but anyways, I will just start my presentation. So, okay. So this is the problem statement. So the problem statement states that a simple helicopter can be made by attaching rotor blades to one end of a vertical stick, and the helicopter moves upwards when the stick is twisted at a high enough speed. So in our case, we believe that this is very important. And then let go. So investigate how the relevant parameters affect the lift off and the maximum height. So the key points are initial velocity, motion, design of blade. Summary of the reporter. So the reporter just mentioned the theory and helicopter, how they designed their helicopter system, and then also Newton's third law, Bernoulli's principle, and also ideal gas and adiabatic system. And his experiment was he used a motor and also used 3D printed blades in their experiment. And for the parameters, they changed the length, width, and angle of the hatch wings. For data, we believe that they lack of theoretical data, and they shows more relationship of the data set. So some advantage for the reporter, he well explained the phenomenon, and he has clear explanation of laws applied and theories, and mathematical function was explained clearly. Some suggestions will be that too much explanation on the theory rather than focusing on the experiment, and they could consider more parameters, and they also did not provide actual observation video of the experiment. They only provide the phenomenon video, which they use their hand to twist the helicopter, but they didn't show us how exactly they let off the helicopter by using a motor. We don't know if they actually did the experiment by using a motor. And for setup, some advantage is that they control different parameters. So there are 3 parameters, and they did a good job on controlling that. And for suggestions, we believe that there are unclear explanation of the setup. For theory, some advantages are that they show different ways, they show different law applied, and they have clear explanation of the theories. However, some suggestions will be that the laws applied are not highly relevant to an experiment. For experiment and data, some advantages are that clear pictures of the parameters were shown, and suggestions will be that they could discuss more on the relationship of the relevant parameters, and there are lack of theoretical data and lack of data explanation. So this is the discussion structure. So first, I will be discussing with the reporter about some clarification of the theory, and then the setup and experiment, and finally, additional parameters that might affect the result. Thank you. Okay, so I would like to ask a question. So can we go to the data page?
Which one?
The third one.
For the angle? Or?
Yeah, for the angle.
No.
Okay.
Yeah.
Can you explain why the average weight of a 20-degree angle is so small? While everyone can see a trend. So 6, 6.4, and 6.9. So can you explain why the weight of a 20-degree angle wing will be so small?
1 second. Yeah, as you can see in this picture, the lift coefficient, as we just mentioned, which directly, if you were concentrating on my presentation, directly corresponds to lift force. And so you can see at the angle of attack, like right between 15 and 20 degrees, it reaches the maximum, which is about like right under 1.75, the lift coefficient. And after 20 degrees, it starts to immensely decrease. So that's why the lift force is so low, because it directly corresponds to the lift coefficient.
Okay, so you mentioned of the lift force. How did you measure the lift force?
Setup page.
Did you use?
Yeah, just 1 second. Let's go to the setup page. No. Yeah, see, there's an electronic scale,
Yes.
right? So before we put on the plastic wings, we have to measure the weight of the whole system, including the motor, the balance point, these twists, the wooden handles, the switch, the batteries, right? Everything. So basically, we put that on without the plastic wings.
Yes.
With this, but without the plastic wings. And so we have a weight route, right?
Yeah.
So basically, we set that to 0. You can't do that in electronic cells. So, and then we attach the wings onto it, right? So then we have the initial weight of the wings.
Yeah.
Yeah. So
And?
go back to the data page. Yeah, any data page. Like so, this is the starting weight, which is the weight of the wings. You can see it's all 7.783.
Yeah.
Right? So basically, we measure how much it weighs after it starts spinning because it generates a lift force, which decreases the weight. And then we take that off 7.783, and then we have the lift force. We take the average out.
So how did you measure the first time?
You have a...
No, because the helicopter is already spinning. Wouldn't it just fly away? So how did you measure?
Go back.
So did you stick the helicopter on the scale?
Give me a second.
Then is this what the problem statement wants you to do?
You know what? This one is sticked onto the motor, right? And
Yes.
then the wings are sticked onto this. I know what you're talking about. You're talking about you want me to measure the maximum height.
Yeah.
But you see, there's something that you can basically use because this one, basically, if you have a force that goes up, right? It goes up and down. So basically, you can measure this maximum height if you have the force and the weight of the thing. It's basic physics.
But did you show the maximum height?
You can calculate it.
No, but you didn't. So you didn't show it, right?
No.
The problem statement states that you have to find the maximum height. Okay, the maximum height.
Yes,
So
I
did
go
you
to
find
the-
the maximum height?
It doesn't say that you have to find the maximum height. It only says how the relevant parameters affect the maximum height, which the maximum height directly correlates to the force and the weight of the object.
So the problem
we can
statement
find
wants you to find the maximum height. So
It doesn't
how do
only
you find
say-
the maximum height? You will have to let go of the helicopter, right?
It only
But did
says
you
to
let go of-
investigate relevant parameters that affect the maximum height itself, but not to find the maximum height itself.
But you didn't. Yeah, you didn't show any maximum height, right?
Yes.
But the problem statement wants you to find the maximum height.
No, that's not what it says. Did it say it
How?
wants to find the maximum height? No.
Affect.
Affect the maximum height. So that means
Okay,
that we can
okay,
just
okay,
find
okay.
the relationship between
The last line shows that investigate how the relevant parameters affect the lift off and the maximum height. Did you lift off the helicopter? No.
observation video.
No.
What do you mean no?
In
Observation
your
video.
experiment, you didn't lift off the helicopter. The helicopter is stuck onto the motor.
Yes.
If it is stuck on the motor, how can you measure? How can you consider like air resistance or other parameters that might affect the result? So you didn't
What do you
consider.
mean air resistance?
You
Air
didn't-
resistance is measured in the drag force, which directly correlates to angle of attack, as mentioned in my
But
graph.
you only measure the lift force, right?
Yes, which directly correlates with maximum height and the liftoff.
No.
What do you mean no?
No. Okay. So you only found the lift force, right?
Yes. And yeah,
But other than that, what did you find as well?
what did I find? I found that the drag force immensely increases when the angle of attack is basically over
Okay, can you
10 degrees.
go to a page where you explain your drag force?
Go down, that, like the last page. Yeah, that one. Mm-hmm.
So this is your drag force, the drag force?
That is the lift coefficient, which directly correlates to the lift force, which is basically.
Can you
You know
explain
what?
how you find out drag force?
Yeah,
Just explain it.
I just want to do this. So basically we have this. CL. And then we have this. Drag force. That is how the formula is written.
Yes, but how did you transfer between them? Because you find out the lift force, and then how do you change it to drag force? You use this equation.
Lift coefficient right up there.
Well, where?
Here, coefficient of lift. Did you concentrate on my report?
No. This is the coefficient of the lift force, but so you change that into the drag force.
Well, we could change it into a drag force, and then you could change it into.
No, but this one is lift force.
No, that one is the coefficient of lift.
Yeah, coefficient of lift. Like how do you change it to? Oh, so let us directly equal to the drag force.
Directly, it directly correlates to 1 over.
Yeah, so it helps you to figure out the drag force. Right?
Yes.
Okay. What do you think of the data? Because you didn't compare with your theoretical data, right?
Yes, obviously that's something that needs to be fixed. Yeah.
Yeah. So you don't know how accurate your data is, right? So maybe your data is completely wrong, right?
We can. Huh? Again? Yeah, I didn't hear you.
You didn't figure out any theoretical data.
Actually, we did. We just didn't put it on here.
You should have put
Yes,
it
I
on
know.
it.
Yes.
You know?
Yes.
Because you need to compare the accuracy of your data.
Yes, and then we could do more error deviations of the theoretical of the comparison between theoretical data.
You know you should have done that. Yeah.
Yeah.
But what did
Because we only just realized that like 5 minutes ago.
Okay, so I think for the next time, in my opinion, you should focus more on the accuracy part and compare with theoretical data.
Yeah, of course.
Maybe the conclusion part is completely wrong if your data is wrong, you know. Okay. So problem statement says that the helicopter should move upward in the experiment, right? But did your experiment show that it moves upward?
Lift force.
No. You have to consider reality, you know.
What? It is done in an ambient environment.
No, because if you're only spinning it on okay, so that's it. You're only spinning it on a stable surface, right?
Yes.
So what if there are wind inside the in the laboratory?
But then that is something we have to cancel out because that will be another thing that we have to consider. That will be another variant that we have to consider, which just makes this experiment a lot more difficult.
Yeah,
and the problem statement doesn't
it.
state anything about wind blowing horizontally.
But it says that the helicopter moves upward, and you also change the color of it, which yeah, it has to move upward. And if it moves upward in a reality, there will be other turbulence affecting the result. But you didn't consider it. Because in my opinion, I think you should consider it moving upward. And if there is really wind blowing affecting the result, then you should have all the data written down. So you have many data points, and then you can find the average of those data, and then find the error bars so that you can know what the uncertainty of the data is.
That would just create more errors in our experiment. That, you know what? Remember
but
in
that
the
is
short
more,
questions you
that
asked
is more
me,
similar to the reality.
which is basically what we did here. Turn to the observation video. You remember, like, play that one. You remember you asked me how it goes back, right?
Yeah.
In these short questions. That is because that when you, can I have a pen? When you release this, you're exerting a horizontal force onto this because you're spinning, right? Spinning. This hand leaves the stick first. This hand leaves the stick first, and then you still have a force that is pushing right there.
Yeah.
Yes.
I understand this,
That
but
creates
this
more
doesn't
errors.
answer my question.
Okay, time is up. The opponent have 2 minutes. Sorry, 1 minute.
Okay,
Summarize your
so
discussion.
in the discussion we just made, I figured a very important question. So in their report, they did find out the lift force, but however they calculated the lift force only. They didn't calculate the maximum height. So they used their calculated maximum height to calculate lift force to find out the maximum height. So their maximum height is a theoretical data. So which means that they only find out the theoretical data of the maximum height. The maximum height is the most important factor in the problem statement. You have to find out the maximum height, but you only chose to find out the lift force and then calculate the lift force into into the maximum height, which I think that is not what the problem statement wants you to do. And if possible, for the next time, if
Okay,
the
time
reviewer
is up.
asks you a question, please just don't
Time is
move
up.
to another question. Yeah, thank
The
you.
reviewer, you have 3 minutes to ask the questions.
So first, I want to ask the reporter, do you think that the time duration of the force acting on the object matters?
Which force? The
And
lift
the-
force or the drag force?
The force your motor gives it.
The force you mean the rotational one?
Yes.
No, it doesn't matter because as you can see in the give me a second. This
Oh no,
So
it's okay. It's amazing.
no, it doesn't matter because of the torque
Okay,
that is giving this.
so how about the lift force?
The lift force.
Yes.
You mean for my experiment or normal conditions?
Your experiment.
No, it doesn't matter because it is maintained at a constant rotation per minute.
I think you mentioned that you can find the maximum height, but by knowing the lift force. But I think that the time duration, the lift force acts on the object also matters the maximum height.
Yes, the duration time directly correlates to 1 over lift force
But I
squared.
think, do you think that it might affect the maximum height?
You mean the time duration?
Yes.
Or any time duration?
Time duration, the force acts on the object.
Yes, because when the helicopter spins up, the lift force
So-
gradually decreases.
So how did you get the maximum height if you don't know the time duration it is acting on the object?
1 second. We have this equation, not equation, a relationship that is T of duration corresponds to the lift force squared. We have this. So basically, if we have the lift force, we can calculate how much time it needs to make the lift force 0. And then we would have an exponential graph.
Oh, it's okay, it's okay. May I ask the next question?
Yes,
Okay,
please.
so do you think the shape of the blade also affects the phenomenon?
Yes, absolutely.
So would you consider it as a parameter that you should do in your experiment?
It is a parameter that can be considered to be put into an experiment.
Okay, so for the opponent, what else parameters do you think affect the maximum height and that they should consider in their experiment?
So one thing I think you just mentioned is the shape, right?
Yes.
Another thing that I think you should also mention the thickness of the blade, because the thickness of the blade will also affect the result. So yeah,
Okay.
that's in my opinion.
Okay, thank you. So, for the reporter, do you also think that the stick under the blade affects the experiment?
My experiment or
Yes, the problem statement.
the problem statement or my experiment?
I think your experiment should be the same as the problem statement because it is what you should do.
Well, I mean, yeah, it definitely does affect because you're exerting another force.
Okay, good.
Time's up.
Thank
You have 2 minutes to prepare. The reviewer.
viewer of hand helicopter. And this is a problem statement, and I will skip it since they already talked about it. And this is the reporter's outline. They talked about their theory, which they applied Newton's third law, Bernoulli's principle, and they quantified the lift force, and they changed their parameters in their experiment to know the results. And their parameters included the length of the wing, the width of the wing, and the angle of the wing. And so we asked them what are more parameters that could be considered. And in my opinion, the shape of the blade would matter. And for the opponent and reporter, they also think that the stick is an important factor in the experiment. However, the reporter didn't consider it when they are doing the experiment. So I think that is what they should consider next time. And when the opponent asked them did they find the maximum height, they answered that they could find the maximum height by knowing the lift force. And the reporter, and in our opinion, we agree with the opponent that they should really measure the maximum height and know what's the difference between the theory and their experiment. And the opponent asked them, did they compare their theoretical value with their experimental data? And the reporter answered that they didn't put it there and they should have put it. And I think they both are correct and they could improve it next time. And when the opponent said that they should consider the wind and other factors affecting the hand helicopter, and the reporter answered that it would just cause more errors. But I think in experiments there must be differences between the experiment and the theory, and they still should do the experiment to try to find the cause of the differences. Like the air drag and other forces might act on the hand helicopter to affect the results. And for the strengths and weakness for the reporter, the strength is that they had a clear explanation of the mathematical equations, and they have clear explanations of the factors they considered and the reason why they ignored other factors. And the weakness is that they have few parameters, which I think they should have more parameters that affects the experiment. And also they didn't investigate about the stick that affects it, and they didn't talk about much about their experimental setup. And also the experiment has small relation with the theory, and they didn't find the maximum height, and I think they can be more rational when they are discussing. And for the strength and weakness of the opponent, I think their strength is that they try to clarify their experimental setup, and they consider other important factors that we also think should consider in their experiment. And the weakness is that I think when they didn't focus about the theory but only the experiment, and I think maybe it is caused by not enough time. But I think when they want to know more about the theory, they could just maybe cut the answer of the reporter if they couldn't get what they want, and ask more about the physics phenomenon of this prompt, and then know more about this question. And this is the end. Thank you.
Okay. Now, the reporter had 2 minutes to make a.
Okay, thank you, reviewer and opponent. First of all, I would like to apologize. I don't think I was that aggressive, but if I caused anything errors, I'm sorry. Okay, so let's check out the problem statement first. Investigate the relevant parameters that affect the liftoff at the maximum height. Notice that the main thing, investigate relevant parameters. Investigate relevant parameters. Okay, next one. Okay, so first of all, why does the hand helicopter move backwards in the video? Because it gives it a horizontal force, and that is something that it causes more errors, because then it will create an oscillation motion and a rotational motion, which basically it just spins the helicopter around. Now, next one. How does the experiment correspond to the problem statements? All results can be calculated, and the opponent seems to have misunderstood the problem statement, which I probably just mentioned. But Yeah, that's a slight problem. The data isn't compared. I did compare the time, but due to report time, the part wasn't put on. Now, the helicopter didn't really fly, consider reality. By using our setup, we can cancel out most deviations cost, which is much more important considering like reality. Would the shape of the wings affect the lift force? You know, the shape of the wings, like basically if it's a triangle or a circle or something like a water drop, it would definitely be a parameter that would definitely affect the lift force, but it cannot be quantified properly since there are so many different things that you have to consider. Yeah. Including the stick. Yeah, the stick basically has the same problem with that. The opponent clearly really isn't familiar with the report itself, as many questions were based on problems with no great significance, and the discussion time was just spent on how my experiment is not the same as in an ambient environment. And that's all my remarks regards to the opponent and the reviewer. Thank you.
Okay, thank you. Now it's time for the jurors to ask a question. Please.
Okay, so in the theory, the reporter used the adiabatic gas to do the derivation, right? So, so first, my question is, please define adiabatic, and second,
Adiabatic.
just a second, let me finish it. And second, how do you rationalize that it's proper to use adiabatic gas?
The adiabatic environment means that there is no temperature change amongst the entire environment as a whole. And the theory itself is just another variation of the Bernoulli's principle that the steady compressible fluid, you can basically change the psi, which would affect the whole thing. And no, we did not actually use this equation. It is just another variant of Bernoulli's equation, Bernoulli's principle.
Okay, so how about the reporter, the opponent, and reviewer? So,
My definition on the adiabatic for the
adiabatic is the definition, and also, I mean, under what kind of condition that you can use adiabatic gas to do the derivation?
Oh, for this one, we actually agree with the opponent. Yeah.
Okay, and then
The reporter,
the
sorry.
reviewer.
Oh, I think it's not that the temperature doesn't change, but that the heat that goes in and out the system is the same.
Okay, and then why that? I mean, under what kind of condition that you can use the? Well, assuming that the gas is adiabatic.
Do you mean that?
I mean, in this case, I mean, if you want to do the adiabatic, do you think it's proper or not?
What would not?
Assuming the adiabatic gas.
Oh, I think it's inappropriate to use the theory here because it's in real case.
It's only sticking on the motor. It's not in the real case. Yeah.
Any other questions? Yeah,
I have
please.
one question for the reporter. You mentioned Bernoulli's principle, right? So you try to imply that the lift force can be calculated by using Bernoulli's principle.
Well,
Yes or no?
no, but kinda, because we
Yes
can.
or no?
No,
Why is that? Then why you mentioned that in your report?
because Bernoulli's principle is. Let me just.
No, okay. So how do you think this Bernoulli principle is adequate for the calculation of the force in this case?
I don't think it's that adequate because you have to
Okay,
consider.
yes or no?
No.
No.
Okay, thank you.
Any other questions from the jurors? Okay. No. Let's get the. Let us start with the score of the reporter. 6, 5, 4, 7, 4, 7. Thank you very much. Next, the score for the opponent. 6, 4, 6, 7, 6, 8.
Thank you.
Finally, the score for the reviewer. 7, 8, 8, 7, 7, 6. We begin with the challenge from the opponent to the reporter.
Oh, we want to challenge number
15.
number 15 rebounding capsule.
Problem 15.
We will accept the challenge.
Okay. Each team, please write down the name of your representative. Okay, 12 minutes.
Good morning, honorable judges and fellow students. I'm the reporter from Team MD Fresh. I'm going to report problem 15, rebounding capsule. So the outline of my report will be the problem statement and then observation, then our theory, then experiment and analysis, and conclusion. So in our the problem statement is a spherical ball dropped onto a hard surface will never rebound to the release height even if it has an initial spin. A capsule-shaped object like a tic-tac mint, on the other hand, may exceed to the initial height, and we're going to investigate this phenomenon. So the phenomenon will be the capsule-shaped object exceeding to its initial height while rebounding the second time. The discussing point will be the energy transfer during the motion of capsule. So our observation is there's some technical issues. So I'll explain the observation later. The theory is that when the capsule is dropping to the impact surface, that's going to be the impact velocity and the rebound velocity, which we can then separate into V1, Vy, and Vx. And then when it is impacting, there's going to be two forces impact on the capsule, which is the normal force and the friction force. But it is not the force is not going to impact on the center of mass, so it is going to give it omega. And in our theory is that if we use FDT, which is the impulse, will equal to the change of momentum, which is m times Vx1 minus Vx2, and because there's going to be two forces, the normal ndt it will equal to m times Vy1 plus Vy2, because this is positive and the first one is negative because the direction of the two velocity is different. And because they're going to we're going to calculate the angular momentum, and if we use y cross FDT plus x cross ndt will equal to the moment of inertia times the omega difference, which will then derive to the calculation will be the angular momentum in this motion. And because it can exceed to the initial height when it rebounds, so it is elastic collision where the energy of omega 1 plus the energy of velocity v1 will equal to the energy of omega 2 plus energy of velocity v2. But under actual conditions, energy will be lost, might transfer to heat energy while colliding. So the actual equation will have to add on energy loss in the second time. So the equation will be accurate. So if we separate v1 into the two directions, which will be vx1 and vy1, and then vx into and the second v2 become vx2 and vy2. So we will derive at the change in the energy change in vx will plus the delta e vy will equals to the energy change of the omega change and plus energy loss will be 0. So because you might say that there's going to the movement will be separated into two directions, a horizontal and a vertical direction. But in our case, there's not going to be a horizontal direction, because from this equation that if we move delta E Vy and delta E omega and the energy loss to another side, which will equal to Fdx from the theory we used. So the sliding behavior will be a horizontal direction motion, which is nothing in our experiment. And this distortion, maybe a distortion of the capsule on the surface, because the contact point might become a contact area when the capsule have a form change. So the material we use is close to rigid body, which will not have a form change. So case one of the motion. So if omega is larger than 0, then the theta angle will be smaller than 90 degrees. And in this case, omega 1 will be larger than omega 2. So, and the change in the omega will be, energy change in omega will be smaller than 0. So the velocity will be smaller because omega 1 is the angular momentum. It has more angular momentum at first, and then it has smaller angular momentum later. So the angular kinetic energy will be transferred into kinetic energy, which will be the reason why it will exceed to the initial height. And in case 2, if this case 2 is that the angular kinetic energy will be smaller. The second after contact, the angular momentum and kinetic energy is still bigger than the first one. So there's only little change in change of energy, of the kinetic energy, because not enough angular kinetic energy is being transformed into kinetic energy. So it might not exceed to the initial height because of it. And then a same direction of motion, omega, and the first omega. This is the same as this one, but it's in different direction. This one will also not exceed the initial height because the angular kinetic energy is not enough. It did not transform enough into kinetic energy, so it didn't have the energy to push it upwards. And our experimental setup. So we release the capsule, and then because there's no angular kinetic energy first, and then it will contact with it, and the force will give it a torque, and then it starts to spin, and the second impact will be higher than the first one. So we're going to track the height of the highest point of the first impact, and the height of the highest point of the second impact. And this is how we check our capsule. So in experiment 1, we release it at the 0.3, and then when it rebounds, it did not exceed to its initial height. This is because of the omega didn't. The slope is how omega changed, and the amount of omega did not transform enough into kinetic energy. Because as you can see, the omega is increasing very. The tint line is the after impact line. And in our case, in our experiment 2, which is the case 1 that I just said, is that it exceeds to the initial height. And the graph will look like this because the angular kinetic energy increases and then decreases into, because the reason of decrease is that it is being transformed into kinetic energy. And in experiment 3, we observe that this will be a case 2 that almost reaches to the initial height, and this is because that the angular kinetic energy is decreasing, and then after impact it starts to increase. So there is not a significant change in form of energy that it didn't change into kinetic energy. So this is the reason why it cannot exceed to the initial height. And in experiment 4, this is the case 3 that we just mentioned. So the angular kinetic energy starts to increase when the first impact was done, and then the second impact, angular kinetic energy also changed into kinetic energy, and it will exceed to its initial height. So there's going to be the reason why of the motion of K3 is because although omega 1 is larger than omega 2, but the energy loss plus the energy change is larger than 0. And this is an extra case that we found in our experiment. It's a double impact motion. So a double impact motion is that when it drops and the contact angle is too big that it didn't have enough speed to go up, then it just rotates and then bounces to the second time impact happens in just a little moment of time. So this will be the change in the angular kinetic energy. So this is, I just explained this, capsule impacts on the opposite side, so omega increases, but the vertical speed of the capsule is not big enough to lift it. So the capsule impacts on the other end, which the omega will decrease, and there is a small change in energy. So our analysis is that we found out that if it rebounds slower is the reason why is because there's not enough energy transferred, and if it had enough energy being transferred, the energy is lost. So at this point, it's the experimental data that we find out that will rebound higher. And this is the actual experimental data that we have in different cases. So conclusion. So condition to make capsule exceed to its initial height is that omega 1 is larger than omega 2, and the velocity at the first impact will be smaller than it, and the change will be larger. A little bit of distortion, and there's a large increase in angular speed and a small vertical speed that would cause a double impact motion. And conclusion that further experiment that maybe we can control the angular velocity by using a shooting machine that it starts rotate the first time that we release it. So thanks for listening.
Okay, 2 minutes for the opponent to ask question.
Okay, so for the reporter, how do you define a capsule shape?
Capsule shape?
Because you didn't show us your experiment.
Okay, so
your experiment.
this is the video. As you can see,
okay,
this is the shape.
And so you said that there's no sliding because you didn't see in the experiment. Is that correct?
Yes.
Okay, thank you. And if the initial angle release equals to 0, will it be the torque when it rebounds? Will the capsule start to spin?
You mean it is being released like this?
Yes.
Yes.
It will spin.
Wait, well, I don't really get the question. Can we discuss
If the contact angle equals to 0 or 90 degrees, will the capsule spin?
No.
Okay, thank you. And in page 6, is the velocity here a vector form?
Page 6, velocity. Yes.
Yes. Okay, thank you. And do you think some of the energy will transfer into horizontal kinetic energy?
That is possible, but we
okay.
Here.
And how did you calculate energy loss?
Energy loss. We didn't calculate.
Okay, thank you. And did you measure the coefficient of restitution and the friction of the surface and the capsule?
The friction of the surface is shown.
Okay.
It is being.
How about the coefficient of restitution?
No.
Oh, okay, thank you. And I think that's all the questions.
Okay, 3 minutes for the opponent to prepare. Okay.
Okay, so thanks for the reporter's report. And dear judges, reporters and reviewers, I'm the opponent from Legal 2. And the topic I'm going to debate today is number 15, rebounding capsule. So I'll just skip the prompt since they have mentioned it in their report. So this will be an outline of my presentation for the next several minutes. First, I will be talking about the reporter's summary, and then the reporter's conclusion. Finally, the strength and weakness. So first, the reporter's summary. So let's say that normal force and friction force influence on the capsule. So the capsule will rotate and maybe bounce into a higher height. And they say that it's elastic collision. And they said that in their experiment, there's no sliding and no horizontal direction. They didn't consider horizontal direction movement. And they said that the motion might be an opposite direction before you release, after you release it, before the rebound. And in the case of the same direction movement, they cannot get to the initial height, and the angular velocity is transformed is not enough. So, and in their report, they didn't have any parameters that they control or change. So now let's talk about the reporter's conclusion. So they say that when the absolute value of omega-1 is larger than omega-2, the phenomenon will happen. And they measure that their experiment is done in a small impact angle, or it will just rotate and will not rebound in a higher height. And next time, they maybe can control the angular velocity. So now let's talk about their strength and weakness. They have a clear explanation of the theory, and they consider the energy loss in reality, and they did quite much experiment, but there are lack of parameters. And this is the end of my presentation, and I would like to go to the discussion. So you said that your capsule is more do you think a lid-shaped capsule will also result in the same outcome?
A lid.
It's like an oval in 3 dimensions.
Can you draw it out?
Yeah. So your capsule looks more like this, right?
Yes.
And do you think this will also lead to another outcome of the?
I think it will be similar to the spherical.
So can you prove it or?
No, because our experiment is based on the capsule, we didn't do oval.
So, but in your theory, you use an oval capsule, or you just use it to
In the theory?
no, last page. With your capsule.
Oh.
Yes,
Oh,
you
this
use
is just a diagram to show the forces.
So you said that it's static friction when it contacts the surface, right?
Yeah.
Yeah. So but and you also mentioned that some energy will be transferred into horizontal kinetic energy. So where do you think the work appears?
The work.
Yeah.
There's no more up here in the horizontal direction as I suggested here because of the calculation we have done
And how do you make sure that the when you film the capsule it's in a single plane, like from the top view of your experiment? I think that you have a camera here and you drop the capsule like this, and it should rebound and it should go into this one. How do you make sure that these are parallel to each other?
we use a tracker to track the motion.
How about what if the capsule bounces like this or like this? So there might cause a experiment error.
But we only measure the height of it.
So you didn't take horizontal kinetic energy into consideration.
Yes, because there's no work done.
So if there is no work, the kinetic energy of x-axis should stay the same. So why does it change? Why does the velocity of x-axis change?
There's no change in x. There's y.
So you mean that if you drop the capsule, it should rebound. Like this is the side view and this is the surface. So you said that there's no change. So if the capsule drop up here, and even it spits, it will just go up, straight up.
No, when we drop it first, there's no angular.
Yeah.
It's not rotating.
Yeah.
So it will just go up because it's
Straight up.
Yeah, because it is only kinetic energy, and then it is being transformed into potential energy and then kinetic angular energy.
Vertical to the surface.
Yeah, vertical to surface.
Okay. How about after the second rebound?
After the second rebound.
When it has the angular velocity.
I mean, this is the first rebound, and then it starts rotating, and after.
But you said that it won't have an x-axis. So it
Oh yeah, it things out here, and then it rotates down, and then it will go back.
Okay. And you mentioned that if you integrate f times dt. So you did mention the x-axis velocity in your theory, but you said that
No,
you
this
didn't.
is the perk. Oh, you mean this one?
These two. But you said that you didn't measure it in your experiment. So
Yeah, because when we consider both of this will become from this. So I don't really get it. Okay, can you explain what you think?
in your experiment you didn't measure the first equation. You didn't measure the x-axis velocity.
That's when there's no work done in our experiment.
So if there's no work done,
Like here. Because there might be the direction you might say the work is in horizontal direction, but we didn't observe this in our experiment. We only have vertical direction.
so how do you compare the initial angular velocity and the angular velocity after the rebound?
How do we compare?
Yes, by the experiment or?
By the experiment. We use the tracker.
So can you explain why this didn't reach zero?
I think. Oh, because this is a center mass.
Okay.
Just go to space.
So do you think the contact angle will also affect this part?
Yeah, definitely, but we are not able to control the contact angle.
Okay. Thank you.
What do you think if we can control the power contact?
I think maybe maybe you can consider so if you have a angular velocity and when it's near a certain, I think maybe you are able to calculate the time when it reaches the surface. Yes, the instant when it reaches the surface, and you can get it, and then also the height of the center of mass.
So you're saying but we don't know where the contact angle the second time because we dropped the first in and it starts to rotate the time at the first rebound.
Yeah.
So we're not able to make sure the second rebound.
Okay. In page 13. Sorry, in page 28. Can you explain why the energy transfer is lost?
You mean energy loss?
Yes. And energy transfer.
This.
Yeah.
Oh, it's because as I've shown there are different cases and there are cases there are cases that energy transfer is not enough. The angular kinetic energy now changed to kinetic energy, so it is still it's an angular kinetic energy.
Okay. And so you said that you can control the contact angle.
Yes.
So maybe I think next time you can make it as a parameter. So your experiment will be more complete.
Yes, we have thought of that, and we think that if we can use a machine that will.
Okay, thank you. And so did you have a comparison between theoretical value and experimental value?
No.
No.
Yeah, because we know our theory is based on energy transfer, not based on force.
So if you have an initial angle, when you drop the capsule, can you predict its movement?
I mean, can we use this theory to predict the movement? No, because this is this is energy transfer theory. Our theory is based on energy transfer, not about motion.
So if you say that you can predict the motion, so if you have all the same conditions when you drop the capsule, do you think the motion will be the same or it will be random?
I think it will be random.
And can you explain why it is random?
Because the force being applied, we don't know the contact angle here, so we don't know.
I mean, all the conditions are the same.
Oh, the first time.
Yes.
You mean first time rebound or it's dropped?
When you drop it, all the conditions are the same. Can you predict the motion?
I think we can predict the first rebound, but not the second one, because the second one will have different contact angle.
Oh, okay. So if you can predict it, why didn't you, get a theoretical value after the first rebound?
Because the problem statement is about the second rebound.
So how can you prove that your theory is right if you can't even compare between the theoretical value and the experimental value?
Because in our experiment it does exceed to its initial height, as you can see here.
But you didn't have an experiment, but you didn't have a theoretical value, so I think you can't really prove it. And next question. So what will happen if the energy transfer into different direction?
Energy in direction.
What will happen if the energy transfer into different direction? Like it's not totally vertical or vertical velocity or angular velocity.
So you're saying that energy will be transferred into horizontal direction. Yeah, but we have proof that there's no from here there's no more from.
And did you measure the chance of happening the higher rebound? So because you said that it's kind of random, although I think it's not.
And because we're not able to control most of the factors in the theory.
Do you have the chance of the phenomenon to happen? Like
the percentage?
Yes.
No, because every time it's different.
I think maybe you can, just
how will you measure the percentage?
Maybe you can just combine all your experiment data together and calculate the percentage. Okay. Next time. So in the problem statement, it says that actually it
Okay, time's up. The opponent have 1 minute to conclude your discussion.
Okay. So the reporter didn't have a theoretical value of their experiment, so they can compare it with their experiment data. Therefore, they can't prove if their theory is right. And they say that a lip-shaped model also will have the same phenomenon, but they didn't take this into consideration and make it as a parameter. And I asked that if there is no work in the horizontal direction, why the kinetic energy should stay the same? So why is there a change? But he said that there's no change. But yeah. And so I asked them if they take the contact angle into account, but they said that they can't control the contact angle even if they make all the situations are the same, the contact angle will be random. But as
Okay,
far as I
time is
see,
up. 3 minutes for the reviewer to ask the questions.
Okay, right. As regards to the opponent and the reviewer, first of all, this question is directed to the reporter. Did you do any sort of data analysis on errors and deviations regarding your whole presentation?
Because we say there's no.
Did you or did you not? It's a yes or no. No?
No.
Wait, no?
No.
Okay. This question is for both of, oh, you know what, first. How did you construct your capsule? Like, what is it made of?
It's made of a kind of plastic, and it is close to rigid form.
It is close to rigid form. Can you please explain why it is close to rigid form and why?
The structure of the material. Like iron is close to rigid form too,
Yes.
but it's not a rigid form. The definition of rigid form is that there's going to be no form change when it is being impacted for something.
So think that your capsule is basically possesses no form change when it collides with the.
Yes, it's close to a rigid form.
Do you think that his capsule is capable of the definition of rigid form, of rigid body?
I think it's not.
Okay, so do you think, for the opponent, do you think that when it collides, is it a elastic or an inelastic collision?
It's not a fully elastic collision.
So it's an inelastic collision?
Not inelastic.
Okay, so
Yeah.
basically between,
Yeah.
in the middle. Then, do you think that regarding his capsule, when it contacts with the ground, will the shape of the whole capsule change?
I think it will slightly change.
Then do you think that the contact area, the contact point, the contact area, you know what I'm talking
Yeah,
about,
yeah.
would it change?
I think it will.
Then would it create friction to provide an extra torque regarding the whole angular velocity?
But theoretically, if your contact area is bigger, the friction will still be the same.
Yes, yes. Then what do you think about this? Do you think that your contact area would change and would the friction affect the angular momentum?
No, the contact area will not change because this is close to rigid form. And you
Okay.
can take the.
One last question. Regarding air friction, and do you think that this is something that should be put into account? Air friction, air drag, air resistance, please, yes or no?
Yes, definitely.
Yes, definitely. Did you do anything like this in your
Yeah, because
presentation?
if
No,
you can-
okay. Do you think that this should be put into account? Yes, okay. I think that concludes my questioning time because my time is up. Thank you.
Okay, 2 minutes to prepare. Go ahead.
Good morning, honorable chairman, jurors, and fellow competitors. I am from Team Erudition, and this is my review for question number 15, rebounding capsule. There seems to be a problem. First of all, the outline of the recording, the observation, there was no observation video, which they cannot describe the phenomenon if there is no observation video. The theory, the mathematical parts are exceeding well. However, the report needs to be more familiar with it since he constantly stutters and looks at the screen. Setup, there was no setup. No, none at all. He did not describe how he flicked, how he released the capsule itself, what initial height it was, what equipment did he use to shoot the whole experiment.
Yeah, technical.
Technical difficulties.
Be careful.
Sorry. Okay, for the experiments, there are clear results that perfectly match the theory. However, there's no mention of how it's done. Like I just said, no setup. The conclusion is in sync with the theory and the experiment results. Brief review. Pros are very clear structure throughout the whole presentation, detailed mathematical parts, but I think the reporter needs to be more concise and familiar with them. An overall success regarding the experiment results being in sync with his theory predictions. The cons are the R-squared value is not calculated in any of his graphs, which may lead to some errors, and he did not do any deviations regarding the data that he collected. The explanation of the whole experiment is very incomplete, as we previously mentioned, the setup, the experiment as a whole. For the opponent's speech, clear speaking, and he asked concise questions that were on point, very important parts that he may miss for the reporter. But the cons are a lot of words were in the same page in the slide, and he asked a small portion of questions that was discussed in the reporter's slide, but that's just a small problem. Now, for the clash, first of all, the x-axis velocity wasn't measured. The reporter mentioned that it was irrelevant since the horizontal axis is not considered in the experiment. Well, the reviewer's point of view is that the horizontal axis should be considered into effect if there is a relative angular velocity, since the torque may affect the whole motion of the capsule. What is the lowest point in the graph of 16.0? They track the center of mass. The reviewer thinks that another point should, aside from the center of mass, should also be tracked to provide more precise data regarding the experiment. The contact angle should also be put into account. The reporter replied yes, but they didn't do it. The reviewer agrees with the opponent and suggests further experiment to be conducted in the future. Are there any theoretical data compared with experimental data? No. The reviewer agrees with the opponent since this is literally the only way to prove that his experiment is viable and accurate. The reporter should actually double check their slides before reporting, since the observation video at the setup is very critical, very necessary to actually demonstrate the phenomenon and this report as a whole. The reporter should explain his theory more properly, like the second impact. Why is there only the second impact? There were only assumptions regarding ellipsoids and collision and energy loss and other things. The opponent overall did a great job in giving the reporter precise questions and some valuable comments regarding further experiments that he may conduct. And that concludes my report. Thank you.
Okay, the concluding remark from the reporter.
So for the concluding remarks, some major points that are discussed is that we didn't consider the work being done in our experiment focused on the energy transfer, not how the force impacts. And the major question asked by the opponent is that can you make sure the contact angle and can you predict it? And we answered that the contact angle of the second impact was not able to be controlled. And no, we were not able to predict it because our theory is based on energy transfer. And why didn't you compare theoretical data and experimental data? And why there's no error bars? The reason why is that our theory would not provide a experiment, cannot predict it, so we would not provide theoretical data. And the graph you saw is that we track it with a tracker, so the error bar will be really slow. And are there any distortion of the capsule during the motion? now the capsule we use is close to a rigid form, so which will not have a form change. And remarks the effective discussion with the opponent was being conducted, and we discussed the future parameters and how we can do the experiment next time. And suggestion for the opponent that try not to discuss some like irrelevant topics like air convection and other irrelevant parameters when they don't affect that much in the results. Thank you.
Okay, it's the time for the jurors to ask the question. Please stand up for 3 of you.
Can I clarify something? When you mean opposite direction motion, what do you mean?
How it spins, how the capsule
What's
spins.
the same direction motion?
It's about the omega, if it is positive or negative. If
The rotation is
yeah, the rotation.
from the same direction as the translation.
No, yes, but we cannot predict the translation because our theory is based on
It
it.
jumps higher only when you have the opposite direction motion.
As we say, if it is we, because the energy change is enough for vertical force. The omega, the rotational, angular momentum and kinetic energy is being changed to kinetic energy, and that's why it is enough to make it like exceed to the initial height.
Every opposite direction motion would jump higher or
Yeah, we yes.
how about do you have
I don't agree with the report. I think that only certain contact angle will make the capsule jump higher.
and it could not jump higher if it's the same direction motion, or it's still possible?
I think, yes.
It's still possible. How about
Regarding the first question, I think that both the contact angle and the translational horizontal axis speed and the height in the initial height in which he released the capsule itself would also affect whether it bounces high enough to actually exceed the initial height. And regarding if the same direction may exceed the initial height, I think yes, it is possible for energy conversion to happen.
have you observed that, or just
Oh, you mean the experiment?
the same direction motion it jumps higher?
No, I have not conducted an experiment regarding this.
Okay, thank you. Any other questions?
So one question for the reporter is the capsule shell object is solid or hollow?
It's solid or
Hollow.
Oh,
It's
yeah.
empty inside.
it's hollow inside.
It's hollow.
We only put some weight in it, so the weight is constant.
So it's empty shell,
It's empty shell at first, but we put things inside to make it
complete solid.
yes.
So
So it's a
if you will you see the same phenomenon if it's hollow? What do you think? Yes or no?
yes.
Yes. How about you?
If the capsule is hollow,
Yes or no?
no, because the
Okay. Opponent?
I believe that if the density is even,
Yes or no?
yes.
Any other questions? Okay. No further questions, so let's get the score. First, we begin with the score of the reporter. 6, 6, 7, 4, 6, 6. The score for the opponent. 6, 7, 7, 7, 7, 7. The score for the reviewer. 7, 8, 7, 7, 6, 8.
Thank you very much.
Any comments from the jurors? How about your comment to the report?
No comment.
Okay. Any other comments?
Just one comment. So
Okay.
when you present something like a reviewer, please focus on physics. Focus on physics.
Physics.
Physics, yes. Don't say that, oh, somebody's not familiar with something, with speech is stuttering. Okay? Don't say that. Don't attack your fellow competitors regarding something that's not about physics.
Okay, thank you
Okay.
very much.
Okay, then let's take another break of 10 minutes.
We would like to challenge question 12, Overforce Pendulum.
We accept the challenge.
Okay. Okay, 12 minutes for the reporter.
Honorable judges, fellow debaters, opponents, and reviewers, good morning. In the next 12 minutes, I will be presenting the prompt 12, Overforce Pendulum. First, I'll go through the phenomenon introduction, and then I'll go through the experiments, results, and analyses. And finally, I'll talk about the summary and conclusion. So first, let's look at the prompt. The prompt reads that a Overforce pendulum consists of a mass hanging from a vertically oriented helical spring. The mass can both move up and down on the spring and rotate about its vertical axis. Investigate the behavior of such a pendulum and how it depends on relevant parameters. And we think that the key point of this prompt is, first is it talks about a vertical oriented helical spring. And then it says investigate the behavior and also the relevant parameters. So this is a footage of a Overforce pendulum. And according to the prompt, we can assume that the basic phenomenon, the phenomenon is that the energy of the device transfers as the time goes by. And next, let's move on to the experiments, results, and analyses. And this is a footage of the Overforce pendulum of our experiment. And this is the an ideal solution simulation, and you can see that the translational potential energy and the torsional potential energy will transfer as the time goes by. And this is our equipment that we used in the experiment. The first is a smartphone camera, and the second one is a high-speed camera, and the third is tripod. And also, this is the mass of our Overforce pendulum, and we use a stand and a spring to form a complete Overforce pendulum. And this is the constants of our spring. And this is a footage of our experiment. So as you can see, as the time goes by, it turns to only rotating, and it turns back to vertical oscillating. And this is our experiment setup, which I just showed you the picture of the stand and the mass and the spring. And we put the high-speed camera below the mass to capture the motion of rotation, and while the smartphone camera on the parallel side of the Overforce pendulum to capture the vertical translational data. And for our formula derivation and theory, we use the Lagrange mechanics to solve this problem. So the Lagrangian writes that this equation, and the first two are the translational and rotational kinetic energy, and the third and fourth term are the translational and rotational elastic potential energy, while the last one, which mainly causes this phenomenon, is the linear coupling form. And by applying the Lagrange equation to z and zeta respectively, we get these two equations. So we can, as you can see, these two are pretty alike, so we can write it into a matrix form like this. And by multiplying the inverse matrix of M00I at the same time, we can get this equation, which is the familiar equation of simple harmonic motion we all know. So assuming a solution for z and theta to be a and b respectively, and cosine omega t plus phi, and the second derivative of the z and theta is this. So we can substitute this two into this equation, and we get that. And by Cramer's rule, we know that a non-trivial solution for A and B is that the determinant of the A matrix should be 0. So we, next page. We get this equation. And first we use the value of for the frequencies that we're familiar with to substitute into this equation so that it is more clean, and we can get the omega squared by solving this equation using the quadratic formula. And we see that there's a plus and minus, so we know that there are two solutions for the omega squared. One is plus and one is minus. So back to our assumption, we know that z of t and theta of t can be any linear combination of all solutions. So we can write these two equations. And this page is mainly just to substitute the b into a, so we can get less unknown variables to solve this problem. And to solve the rest of the variables, which are a and phi, a1, a2, and phi, we use the initial conditions of the Overforce pendulum, which at start the z displacement is z naught, and the velocity of z is 0, and same as the theta. So finally, we get this kind of complex equation, but it perfectly describes our Overforce pendulum's motion. So for the experiment, we changed we changed the moment of inertia, and we experimented with 3 different configurations of the mass with 3 different moments of inertia. But we maintained the mass as same, so there are only one changing variable. And first, this is the first moment of inertia I just showed you, and this is the observed motion, while the red line, red dot actually refers to z of t, and the kind of dark green dot refers to theta of t. And as you can see, it does not couple completely as the ideal theoretical result. And by using the equation we just derived, this is the simulation of it, and we can see that the z of t really just don't want to completely couple with the other one. So we increase the moment of inertia, and we can see a better trend of coupling better with z of t and theta of t, and this is the simulation, theoretical motion of the this moment of inertia. And finally, we get to when the moment of inertia is 4.44 times 10 to the negative power of 4, and we get this observed motion where z of t is, we can say it's almost completely coupled with theta of t, and while the and this is the theoretical motion, so we can see that it's also completely coupled. And I'll put back to this. And just to clarify that the theoretical motion, the damping phenomenon is based on the observed motion. So that part isn't really theoretical, but just to make this theoretical motion more easy to compare with the observed motion. So we specifically chose when the moment of inertia equals to that, so that the rotational frequency matches the translational frequency, which is the when we substitute in the omega z and omega theta. And as you can see, the energy conversion is demonstrated best in under such conditions. So when in the green shaded part, it is greater in translation while almost none in rotation, while the pink shaded part is vice versa. So why is the energy conservation demonstrated most effectively when omega z equals to omega theta? It is because that when they are equal, the period of linear and rotational motion of the spring are also equal, so they can transfer better in the Overforce pendulum. And the damped motion The spring motion demonstrates that an exponential decay which can be attributed to damped motion caused by air resistance and internal friction. So this is the theoretical calculation without damping motion. As you can see, it's just keep transferring and it just never decreases. While this one is the exponential decay form. Alright, so in a conclusion, in a Overforce pendulum system, energy converts between elastic potential energy, torsional potential energy, and also the gravitational potential energy. And the second is that the energy loses over time exponentially due to the damped resistance. And by adjusting the moment of inertia of the mass, it can result in the same angular frequency between rotation and translation. And this is the references, and thank you for your attention.
Okay, 2 minutes for the opponent to ask the questions.
Okay, so I have some short questions for you. Excuse me.
Yes, sorry.
So according to my understanding of the report, when the mass increases, the frequency lowers. Is that correct? Is that correct?
Mass increases frequency. Yes, that is correct.
Okay, that is correct. And does the K affect the whole experiment, like the spring?
Yes, it does.
Yes, it does. And how do you think it affects the experiment?
According to our theory, this page, you can see the impact when you change K.
Okay. Okay. And was the mass of string considered in this experiment?
Yes, it is considered.
It is considered.
The M in here means the mass of the figure I just showed you, and the effective mass of the spring.
Okay. And is it a constant?
It is a constant.
Okay. Thank you. so I'm the proponent for topic number 2, Overforce Pendulum, and here we go. So let's talk about the reporter's observation. It is a short observation video that demonstrates the phenomenon clearly, but there is too little description about the whole phenomenon thing. Okay, next page. And let's talk about the theory. The theory has clear illustration to represent the phenomenon, and it properly applies mathematical methods into physics equations. But there is also no background explanation, and it lacks theoretical data comparing with experimental data, and complex equations that may lead to miscomprehension. Now let's talk about the setup. The pictures of the equipment are clear, and there are simple experimental equipment that can be conducted very easily. But if you use a complete setup to describe the whole thing, I believe that it will be more clearer to us. Okay. Let's talk about the experiment. So there is obviously a very logical structure, very solid structure of the experiment, and it applies to the phenomenon. But the effect of the energy decay was considered, but it was not playing like a real role in your report. And there were unclear graphs of the experiment data, and it is quite hard to understand, and you did not compare it with each other side by side, so it may also lead to some miscomprehension. And the deviation of experiment data, the exact things, were not really discussed. Let's have a brief conclusion about your report. And of course, this is a report well structured and thoughtful in many ways. There are still a few flaws that we would like to point out. So first of all, the background explanation should be included regarding the complex equations that you guys provided for us. And the energy decay should be considered in a more heavy part, in our opinion, due to the matter of the experiment itself. It gets affected very, very easily. Okay, so the graph should show more occurrences, how this is affected, how that is affected, yeah. And when it comes to accuracy and precision, we are sure that these are the points that would matter the most. And I would like to begin my discussion part.
Sorry, can you let me clarify something?
Please.
You said that I did not compare my, my theoretical data with my experimental data. I think I'm not clear enough is that this graph is just drawn by the equation I showed you. So I think I did do that part. Yeah.
Okay, I actually meant a more precise comparison. Okay, so that's just a little point. That's not. Yeah, it's alright. If you didn't, then I've got no points against it. So okay, I have some small questions for you. Is the mass horizontal to the ground?
Mass?
Yes.
Horizontal?
Yes.
Mass, you mean by the value of mass or what?
The direction.
Well,
no, this is just a simple setup yes/no question. Okay.
Well, I don't really get your point.
Okay, then we'll skip this one. What kind of spring did you use?
We use an helical spring, and I think that's the description of it.
Okay. Does the K value change when the spring is going up and down or twisting?
According to our measurement, it nearly doesn't change.
But consider this, because the force twisting and moving in a translational direction. So, is there some possibility that it may cause deformation of the spring and affect the results?
It may cause, but in our measurement is that the R square is up to 0.9991, so we think it is negligible.
So you guys think that because you didn't really see the difference, so it's okay. It's
yeah, I think it is negligible.
okay. Yeah, how about the twisting of the spring? Like this, the spring, like it definitely twists, right?
Yeah,
Yeah, and did you consider that?
consider the twisting of the spring.
Yeah, of course it may cause deviations.
You mean the twist of the spring may cause the K to be different? I think that does not change the K.
You think that does not change?
Well, we did not measure it, but I think theoretically it does not change the spring constant K.
Okay, I have to disagree with you here, but we'll move on. It may be easy to have deviation when placing the initial condition. And so what did you do to reduce the effect of deviation?
Like what kind of deviation can be more precise?
Every kind. Anything is okay. Just like
Okay, so first we did multiple experiments to assure that our data was like not just one time and it's like lucky or what. And second is that we like try to reduce the horizontal oscillation, although there are still a little bit, so you can see that some of the back part of the observed motion and the theoretical motion are not exactly the same, so that could be a deviation. But
and I'm asking here, like, how do you like try to prevent those deviations? Like, what did you do to kind of lower the deviation cost?
Well, we try to release the mass from a completely vertical axis, so that it will have the least horizontal oscillation.
Okay, but even if you like release it like very vertical, so vertical, but is there a chance that the spring may still kind of like swing?
Yes, and it is observed in our observed motion, so that I said that the back part of the observed motion consists of a little oscillation of the horizontal
And was
motion.
that calculated into your report?
It was not calculated in our theory because we think that it would be even more complicated.
Yeah, because of course the theory should be like under ideal conditions, right?
Yeah.
But when we do those experiments, like these are like definitely points to consider, since they will definitely happen because we don't live in an ideal condition, right? Yeah, so I think that's a point. You might want to add something to your theory. That's like my little suggestion for you.
Okay, I will try to improve it next time.
Okay, so there may be deviation of the position of the mass and the twisting angle due to the position of the camera. And did you ensure that the camera angles were 100% like vertical, horizontal?
Of course not 100%, but we did it as like the best we could do. So
Okay, so it's quite accurate in your opinion.
yeah, I suppose so.
Okay. And can you like kind of isolate the two modes, like the spinning and the moving up and down? And is there any difference of the graphs drawn between them?
What do you mean by isolate?
Like take them apart and compare them side by side. Is there any difference or any conclusion other than what you have discussed?
You mean the different colors?
Yes.
Like take them apart,
Yes.
and then what do you compare it with?
Compare them with each other.
Then why don't you just put it in the same graph and compare it with each other?
Okay, so what conclusion? Like what? Oh, this is so hard to explain. So, what additional information can you get from this graph? Additional ones. No, you talk about this. I know, I understand. And
Yeah.
what additional information?
Well, I mean, this is basically just what the prompts want us to talk about.
Okay.
So I think this is enough to explain the Overforce Pendulum phenomenon.
Okay. And can you explain the reason for the transformation of the energy?
It is due to the linear coupling form as I just showed you.
Excuse me?
Turn to that page. Yeah, it's the last form, the linear coupling form, which combines the z of t and theta of t together so that it will affect each other.
So that they will affect each other.
Yeah.
And could you elaborate more, please?
Next page.
Can we use like the blackboard or something?
Well, it's like a mathematical. Yeah, it is like a mathematical equation, and that I think we can get it precise and a precise explanation by using the equations here.
So according to you, this is like more of a mathematical problem than a physics problem. Am I correct?
Well, if you are to analyze this mathematical problem into a physics process, you can see that the m times the acceleration of v, which represents the total force. And if you move the two terms to the next side, you will get that these two are actually right. So I think I'll just write it here. Okay. So that the two equations are similar, so I'll just go through one. Okay.
Okay.
So the m times the second derivative of v equals to the total force acting on the axis, and then it equals to like this, you can explain it as a force.
Okay, I understand.
Yeah.
I understand now. Wait a moment, please. And what do you think will happen if the frequencies, they are completely matched, like they are completely synchronized?
Well, I think that is in our experiment where in our third moment of inertia, this one, the omega z equals to omega, basically just equals to omega theta, but there may be a very little deviation. So it will like almost completely turn to the other phase of like the translational or rotational phase, and then turn back.
Okay, so in your opinion, they will be like completely oppositely synced. Am I correct?
Like like this graph here.
Okay, so yeah, and the other graph, it was like deviation considered, right?
Yes.
Right. Okay. That was nice job. Those are my questions for you. Okay, so overall the reporter did I think pretty flawless jobs with only a little error for me to point out, and those are like really minor errors such as like the swinging of the spring. I still think that it should be considered, but of course it is very hard and to calculate it, and it's important to be considered. Yeah, and it was like kind of lost in the whole thing. And about the K value changing, I also think that it should be considered. And the reporter said that they did not observe it in their results. So I think that is an acceptable answer. So good job. Okay, that's my conclusion.
Okay, 3 minutes for the review. Do you ask the questions?
Okay, so great job for the discussion with opponent and reporter and a great presentation. So reviewer is quite curious about how do you measure the delta.
So for delta, we use a object that is known for the moment of that we know the moment of inertia. For example, a rod. which we can already know the moment of inertia. And we twisted it at a very little angle and see the simple harmonic, the angular simple harmonic motion and test the period of it. And by using this equation, and by testing multiple
Okay, and I
objects,
see
yeah.
it.
Thank you.
And please turn to page 20.
This should not.
So in this experiment, you changes the moment of inertia. So, and you said you maintain the mass.
Yeah.
So how do you maintain the mass?
Here, as you can see, these two are screws, and these are nuts and the applied weight. So we like screw in or out of the screw to change the moment of inertia while not altering the mass.
Not the stick in the middle is always the same length.
No, yeah, it is the same as, but the screw, you can screw in or out, right? Yeah, so we can change this part in or out.
Okay, I see that point. So in your presentation, you said power energy will decay, right?
Yes.
So what type of and as the opponent said, it will have some kind of wiggling or something. So what kind of motion, except for wiggle, do you think is affecting the energy decay?
I mean, wiggling as in swinging or something?
Yes. Except for these things, what else?
Of course, the air resistance, but that is like very, very small since the springs are so big. And what's more, the friction, like the top of the spring, like it might create a disturbance of the motion, you know. Yes, and I've observed that in my experiment.
How about you?
I think that like I agree with this opinion and that.
Hands up. 2 minutes to prepare for the review. Okay, 4 minutes.
Okay, so great job to the presenter and the opponent. So this is the reviewer from MD Fresh. So we're talking about Overforce Pendulum. So we won't say it again. So overview of the reporter. The advantage is clear observation of the video and well-struck experiments. Also, delta, a detailed material table, and many detailed mathematical function explained. and explains the theoretical data. And the suggestion for the reporter is lack of explanation of the phenomenon, also lack of parameters, just K and delta. And the force of the hand while letting of the pendulum wasn't considered. Also, lack of explanation of the experimental setup. Details of the experiment we're providing would be better. Also, they didn't consider energy decay. Lack of explanation of the differences between the theoretical data and experimental data. We suggest that they should compare these two data together. Also, lack of units in the sum of the graphs. Overview of the opponent. The opponent's advantage is ask critical question and point out the critical problems that we consider is very great. And also they ask about the energy decay, which is the most critical problem. The suggestion for the opponent is hold on to critical problems and just keep asking that kind of problem and just move to next problem while you didn't understand it. And ask some irrelevant question that had already been explained clearly by the reporter. So need to be pay more attention to the presentation. Also, the suggestion is lack of your own opinions. So here are the major discussions. So opponent asks, what did you do to reduce the deviation? And reporter said that we did the experiments multiple times and tried to release the spring at a vertical angle. And at the reviewer's opinion, the weights being provided didn't help a lot to reduce the deviation. For example, you can't make sure that the spring is released at a vertical angle if you try to release by hand. Okay, so next is the spring constants. Opponent asked, did you consider the deformation of spring? So the reporter said it's too small and won't affect at all. In our opinion, disagree with the reporter. We think they should consider that. Discussion 3. Opponent asked, would the twisting of the spring change the K value? And the reporter says no. But our opinion agree with the reporter. Based on the formula, it won't affect the K value. And the opponent asked, what is the angle of the camera? Is it completely horizontal? And the reporter said that it's not 100% horizontal. And in our opinion, disagree with the reporter. The angle of the camera can be adjusted by using anchoring level. Then next, opponent asks what is the reason of the transformation of energy. And reporter says that because of the linear coupling form. And our opinion is completely agree with the reporter. So here's our conclusion. Good discussion overall and major questions were discussed. Points missed is energy decay, the energy transfer efficiency, filming angle and distance, and the way used to release the spring was not accurate. Thank you.
Okay, finally, the concluding remark from the reporter.
Thank you for the opponent and also the reviewer. And for the concluding remark, I would like to mention several things. First, when we use the the third moment of inertia, the rotational frequency and the translational frequency will be nearly the same, so we can observe the most amount of coupling. And then we try to release the mass in vertical to avoid the deviation, but but like the third part is that we will try to include the deviation of oscillation in our experiment in the future. That is a point we can improve. But however, it will become another situation, but we can still try it. And the transformation of energy is due to the linear coupling, just as also the reviewer agrees with us. And that the friction of the spring and also other drag forces cause the damping motion. But we would like to find out the cause of damping motion in the future. And here are some of our hypotheses. Is that one of it is that the friction of the spring itself, and also the air resistance or the air drag forces, and something like that. And in that, I would like to apologize to the opponent that some of the questions I don't really understand, so I couldn't answer. And that is basically all my concluding remarks. side-by-side comparison. Yeah, thank you.
Okay, now it's time for the jurors to ask the questions. Yeah, please.
Okay, so first to the reporter. So it's clear that the coupling is the key for the transfer between the acceleration energy and rotational energy. So first I want to ask you, what do you think is the physical origin for this coupling? And then second, what's the reason for you to use a coupling that is only linear in the theta and d?
Regarding the first question, we think that the origin, which is that, and also the other equation, we think that is the difference between an ideal spring and a helical spring in reality. Since like when you stretch or squeeze the helical spring in reality, like it, every point of it will be not the same, and it will produce a torque, or when in the rotational form it will produce an up or down force. And for the second question, we actually are not very sure about that, but yeah, but because it matches our experimental data, so we think it is suitable to use the linear coupling form.
Okay, then how about the opponent? Same question.
Same question. I think I agree with the reporter's first question, and about the second question, I really haven't thought about that. So you can see I didn't ask the question. So let me think about it. Yeah, I can only say it is suitable because the experimental data matches, but that is not a very good reason.
Okay, and then the reviewer.
We agree with the most of the question.
Any other questions? I have a question, starting from the reporter. If we add some mass to the bottom, what will be changed?
Like
without say the dimension of this one doesn't change, except for the central mass. For example, the data like this will have anything multiplied.
Yes, like when the mass changed and the moment of inertia also changed due to the equation, like I equals m times the square of the effective radius. So, but when the like the omega z does not equal to omega theta, then it will not be such complete coupling with the two motions.
So they might change.
Yeah, it will change.
What's your opinion?
I agree that it might change.
What's yours?
When you use
Say I just stick a spinner with some plate, whatever material, but with additional mass attached to that, to the bottom. Then how these two curves will be changed?
We think that the period will be bigger.
Both of them?
Yes.
Simultaneously, proportionally, together. So in that case, the pattern will be different according to your answer.
Yes.
Thank you. Now, it's the time for our scoring. So let's start with the score of the reporter. 6, 7, 6, 7, 7, 6. Followed by the score of the opponent. 6, 7, 6, 7, 7, 6. Finally, the score of the reviewer. 7, 7, 6, 7, 8, 6. Any comments on the jurors? If no, have a good time when you're done.